Today we're starting notes about projectile motion. And projectile motion is actually kind of easy when we break it down. We've done a whole lot of things in terms of free fall, throwing things straight up and down. Projectile motion means now we just start shooting things out in a horizontal direction. And sometimes that includes a lot of vertical information. The way I'm going to start talking about this makes sense because if we're in outer space or on a hockey table or on ice, like ice skating, I'm going to start with 7th grade stuff. An object in motion.
Stays in motion.
Okay, unless
Acted upon by an outside force.
Okay, so an object in motion stays in motion unless acted on by an outside force. What's our outside force? Gravity. And that will be our only outside force as we undergo projectile motion. Otherwise, we're not strapping rocket engines with projectile motion because we don't want to deal with X and Y's changing. We're only dealing with a horizontal motion. So as it moves forward, as something gets pushed, it moves and just keeps going. So this cannon, if we have a gravity-free path, if I'm not worried about gravity at all, it has a speed. And what do you notice about the distance and interval between these horizontal?
They're seconds. Or they're constant intervals.
So they're constant, they're regular intervals, and it just glides forward and forward and forward. Kind of like if you shove something on a frictionless surface on as icy of a surface as you can. Or if it was on a hockey table, right? An air hockey table, where it just glides forward. What do you notice about this cannonball right here? This is just something being dropped, right? So talk about its motion. Starts with how much speed?
0.
It starts with 0 speed, and it picks up speed based on gravity. Okay, so what actually happens when I shoot a cannonball is it doesn't go forward. It drops because of gravity, and gravity is only in the up and down direction. So when I talk about the way it moves down, the vertical motion, we have things like x equals VIT plus 1/2 AT squared. We have things like VF equals VI plus AT, and VF squared equals VI squared plus 2AX. And if I was moving forward and only forward, the only equation that I care about is how it moves in the x direction and its speed. And that will only be this equation. Technically, you could say 1/2 AT squared, but is there any acceleration? That makes this whole side 0, okay? So there's no acceleration right there. If that acceleration is 0, then this is all I'm worried about. And that's its forward speed. So the side to side is very easy, and the vertical is everything we've done. The other things and math tricks that we get is if I throw something and launch something at an angle, I could break this into its side-to-side motion and talk about its side-to-side speed, or I could talk about its vertical speed. And this diagonal speed is broken into its components like that. Not only that, but what do you notice about the time of this whole flight? It's 8 seconds. What do you notice about it, the time at the highest point? It's half of that 8 seconds, yeah. So there's going to be a lot of symmetry that this item will land with the same speed, because also it is going down and forward just like this is going up and forward. So it'll land at the same speed. It will have the same height at this given moment. So your change in height is 0 between here and there. Up here, it's its highest point. What's its speed at the highest point? No. VIY is 0. But what kind of speed is it? Its speed is equal to its horizontal speed. It does have speed. It's a non-zero value. It's just only completely its forward speed. A different way of talking about it, right? We have to adjust for the fact that it is still moving forward. And it's still, what kind of shape is this? Because what is linking that also had a parabolic shape? What is linking the x versus the y? Motion. Huh?
Gravity.
No, gravity only happens in the up and down direction. It only happens in the y direction. What is the link between the x and the y? I'll give you a hint. It's the dashed lines. Or the dashed lines help represent it. I heard it. Time. Time is the link between the x and the y. So when it hits the ground, the problem's over. If it hits a wall, the problem's over because something's going to change about its current mathematical trajectory to where I have to either recalculate a new trajectory after a bounce or something, right? So I only care, and the problem stops when it hits something, when we call time, when it's at its highest point, the time is the same between the x and the y at that moment in time when we do our analysis. So here's all the rules. Horizontal and vertical motion are completely independent of each other. Therefore, velocity of a projectile can be separated into its horizontal and vertical components. What am I talking about? What am I talking about? Sokotoa, right? So I can break it into its parts. Projectiles always maintain a constant horizontal velocity, neglecting air resistance. So that's what we said, that the equation is one equation, and it's super easy. Projectiles always experience a constant vertical acceleration, negative 9.8. So it's just like our free fall equations. The only variable shared between both is our link is time. Every point on the trajectory is the vector sum of the horizontal and vertical components. So if I wanted to talk about the speed as it hits the ground, its speed as it hits the ground is the diagonal speed. The speed with which it hits the ground is a vertical speed. Whoa, what? The speed which it impacts the ground with is its vertical speed. The speed that it has when it hits the ground is diagonal. And it's just English. Just the way I phrase it in English. That's a hard part. So I could ask you for the current speed. That's a diagonal issue. This is called the resultant. For a projectile beginning and ending at the same height, the time it takes to rise to the highest point equals the time it takes to fall back to the original height. And objects dropped from a moving vehicle have the same velocity as the moving vehicle. So if a package falls out of a plane, that sounds like a problem prompt. Okay. If somebody is running and drops a tennis ball, that tennis ball is going to be moving forward with them until it hits the ground. On first impact is when it slows. A maximum range for a given initial velocity is obtained when an angle for projection is 45 degrees. This is only also when it lands at the same height. Okay, so if I put something on a platform, this changes things. If I'm trying to shoot something up to a balcony, it changes things. But if I have a maximum range at 45 degrees, I'm talking about something that starts and ends at the same height, like a football field, like a ball getting kicked off the football field up and then back down. That means it's landing at the same height it was launched at. A satellite is a projectile in a constant state of free fall around the Earth. So if I have a planet, Earth, and I launch the moon over the Earth, a satellite, I just missed the Earth. Well, what happens around somewhere across the top of this? I gotta change my perspective. And so now I'm launching it from here. It's got that speed and it gets launched over the Earth. So it's like it's falling towards the Earth. It just constantly is missing the Earth as we shift our perspective around this. It is always going over the Earth, but misses the Earth. It's always going over the Earth, but misses the Earth. It's always going over the Earth. Sorry, it's way down there. It's always going over the Earth, but misses the Earth. So that's a satellite. In order to solve projectile exercises, you must consider horizontal and vertical motion separately. All the kinematic equations you learned can be used for projectile motion. So that's why I put them here on this picture to talk about how it falls, 3 equations, versus how it moves forward, 1 equation that we need. What happens to our 2 other equations? What happens to this equation if A is 0? What is it telling us? If A is 0, and then the same thing about VF squared equals VI squared. Okay? So that's why when acceleration only happens in the up and down direction, the forward and backwards is really easy to do kinematic equations with. Okay? So then let's start with some of our samples, our examples. People in movies often jump from buildings into pools. A person jumps horizontally from a 10th floor into a pool 5 meters away from the building. So we have our building. How tall is this building? 30. And he lands in the pool. How far away is the pool? This is my person. That box is my person. How far away is the pool? So that distance is 5 meters. Find the time and the person's in the air. Is the time, if the person launches like this, is the time a vertical issue or a horizontal issue? Vertical. When it hits the ground, the problem's over. When he hits the water, the problem's over. My bad. I didn't mean to make it sound so violent. Find the time the person's in the air. What equation do you want to use? Yeah, x equals VIT plus 1/2 AAT squared. This VI, in what direction are we worried about right now?
That the initial is a horizontal direction.
All of these are vertical issues, so I put a little y to talk about up and down. Right? I put a little y to just say it's a vertical thing, like an XY graph. Find the time the person's in the air. What's the y value? 30 equals, what's the VIY? What's the initial speed up and down? 0t plus 1/2 -9. Oh, it is -30 t squared. It's -30 because he's falling 30 meters. So his change in position is -30. I could put an arrow in front of that. A triangle in front of that. So we have -30 divided by -4.9 equals t squared. So the square root of 30 divided by 4.9 is about 2.5-ish. I'm going to put 2.4 what?
474. So 47.
2.47 seconds, yes, time.
Oh, I said 6 seconds.
No, somebody said seconds. I wasn't listening to you, David. I'm just kidding. I don't tend to. I'm not going to finish that statement. What are you implying? Vx. Hey, wait, what happens with the velocity in the x direction? X equals Vx times t. We know that we're working 5 meters away, and we're looking for the speed, and so we need the t. When the problem stops up and down, the problem stops side to side. So 5 divided by 2.5 is 2, so this is going to be slightly bigger than 2. Meters per second. All right. What's your link? Time. Cannonball is launched at 15 meters per second at an angle of 35 degrees. Find the x component of the initial velocity. So what's happening here? I have a cannon. And the cannonball. And its initial speed is. And its initial angle is. Is this 15 meters per second X or Y? It's both. Good. Why? How do you know? What gave it away? Yeah, it's diagonal. It's 35 degrees, guys. So when it gets launched, it's probably at ground level, and then it lands roughly around the same height. X component. Vx equals Vi cosine theta. Is that what we talked about last week? Vy equals Vi sine theta. 15 cosine 35 versus 15 sine 35. I don't have a calculator. I'm too lazy. Something's wrong with me. I don't know. Help me out. All right. So we have our components from our calculator. We made sure that our calculator was in degree mode. Then we did trig. How long is the ball in the air? How do you do this? I can think of two ways to do this. What do you need to have in your equation? Guaranteed. Time. What equations have time? Is the flight time a vertical issue or a horizontal issue? I mean, like, which one controls it? Which one says that the problem stops? Vertical. Okay, that's why we're using the longer equations, right? And so if I'm talking about this, I'm going to put y's next to it. And a of y. What's the initial speed? What's VF? Negative 8.6. Why? When we were drawing our displacement versus time picture or our representation, the slope is the same, which indicates speed. You could say that our graphs, our images are symmetrical, that the flight is symmetrical, and so that the launching speed is the landing speed, because you're going to spend the same amount of time going up that you are falling, that it is symmetrical on both sides. So 17.2 divided by negative 9.8 equals t. And I think it's like almost 2. 1 point what? Okay. Seconds? Okay. Does this equation work? What's my change in my height from beginning to the end? 0. And so VIT plus 1/2 AT squared equals 0. I could say negative VI T equals 1/2 a t squared. What's the math trick that you want to use next?
Cancel out a t.
Divide both sides by t. And now I have, what's my launch speed? 8.6? Negative 8.6. Wait, you're telling me I'm going to take my negative 8.6, I'm going to multiply it by 2, then divide by 9.8, and that will give me my t. I feel like I'm doing the same math at this point. Because you are. We took our 8.6, you added it to itself, and then you divided by 9.8, and that was your t. At this point, we're at the same math, 1.76 seconds. Why? Because it's symmetrical at this point. I think that's the best answer I can give you. Symmetry on symmetrical problems will end up with a lot of little math tricks that you can use. You just have to make sure that you write down or describe how you used it or why you used it, or give me an explanation or some sort of idea of what's going on. Mathematical explanations and derivatives work as well. How high does it travel? Wait, am I talking about the end of the problem anymore? No, I'm talking about the middle of the problem. Not the flight up, not the flight down, but from beginning to the middle, or the middle to the end. That's another way of thinking about it. There's multiple ways to do this. How high does it travel up? What equation do you want to use? I would not use this. This is not my go-to. My go-to equation is VF squared equals VI squared plus 2AX. That would be my go-to equation. Because our VI is what? No. What's our launch speed? 8.6, right? And then our landing speed is 0 at the highest point. Plus 2 times negative 9.8 times x. So I just take 8.6 squared and divide by 19.6. What would you have to do if we halved it? Time by 2. So 0.88 seconds. You might also just say t 1/2. That's what I would say. Half the time, right? So 0.88. 0.88. What's VI? We've been using it. 8.6 plus 0.88 plus 1/2. Hey, you want to know something kind of weird? Do we get the same answer? My answer is what? 3.77, right? On this side, it was 3.77. On this side, you're going to get 3.77. Do you want to know something weird? Just this right here is 3.77-ish. And just this over here is 7.57-ish.
So that's the total distance you travel. That's the height.
Why is this the distance as well?
Because it's your acceleration.
Sorry, this is negative, right? Why is this the distance as well? Huh? Yeah.
You can go in half.
This is the second half of it, or this is the free fall component of it. This is it falling down. That you would use this if it was just falling. It has no starting speed if you talked about just the second half. It'd be negative 3.77. Oh, so that means this is always double of what we're looking for. Yeah, because if you have a parabola versus its straight line version of it, the straight line at this moment would be half the total height. And at the end, you would go up 4 times the total height if you went straight line. That's just symmetry. I don't know how else to describe it. I don't know how the geometry works out. That's for you to figure out and describe. I just know that it works out like that. I do know. I just don't need to take the time. That's the secret. What's the range? How do I find the range? We need what time? Which time do I need? The 0.88 or the 1.76?
Range is the height.
Is it just the height?
No, the range is how far down range it went. So range will be x in the x direction is equal to the range.
So it's domain.
No, because the domain is time.
Oh, okay.
Right? So they're both relative to time. And so it's weird because we're not using the mathematical range. I'm saying like down range, home on the range, like field, like how far are you if you're on the, should I say it, shooting range, like the 200-yard line, things like that. So range I'm talking about right now is like horizontal distance, which is what I said here. X in the x displacement in the x direction is our range. Okay, so what is the range? How far does it land? What do we need? X is equal to Vx times time. That's it. Do we have the Vx at the beginning? 12.29. And the time? We saw for the time 1.76. I don't know. You can do that. That's not hard to multiply two numbers together. Wait, do you need me to confirm it? It's like 20-ish?
21.
Okay. If a cannonball doesn't reach the target, how can you increase the range that it goes?
Increase the angle.
You can increase the angle up to 45 degrees. What else could you do?
You could decrease it down to 45.
It's at 35 right now.
Shove more gunpowder.
So more VI. More VI, more angle, up to 45.
You can increase the height.
And launch height. Yeah, you could put it. Oh, you're telling me that I could launch it on a platform 2 meters high?
Yeah.
That's for Monday.